Welcome to all of you. Now we discuss MCQ of paper CC-12 2021, semester 5, group theory 2 and linear algebra 2, mathematics honors, University of Calcutta. Question paper CC-12 2021. Question 1a. Largest order among the elements of Z30 cross Z20 is what? Correct option is 360. Let order pair A, B belongs to Z30 cross Z20. Then A belongs to Z30 implies order of A divides 30. This implies order of A maybe 1, 2, 3, 5, 6, 10, 15 and 30 because order of A divides 30. So the all divisors of 30, and B belongs to Z20 implies order of B divides 20. This implies order of B may be 1, 2, 4, 5, 10 or 20. Now order of the order pair A, B equal to LCM of order of A, order of B. Now LCM of 30, 20 this equals to 60, and LCM of 15, 20 equal to 60, etc. Hence the largest LCM among the possibilities from this order of A is this, order of B is this. So largest LCM may be 60. Example, class 1 and class 1 belongs to Z30 cross Z20, and order of class 1, class 1 equal to 60. So correct option is 60. Next question 1b. Let G be a group of order 77 and A be an element of G of order 7. The number of conjugates of A is what? Correct option is 1. Order of G equal to 77, and let A belongs to G be any elements such that order of A equal to 7. It is given A be an element of G of order 7. Now we know that if G be a group of order PQ where P, Q are primes such that P greater than Q and Q does not divide P minus 1, then G is a cyclic group. Now order of G equal to 7 into 11 because it is 77, and 11 is greater than 7. Here 11, P equal to 11 and Q equal to 7, and 11 and 7 are primes where P, Q are primes, and 7 does not divide 11 minus 1, that is 10. Q does not divide P minus 1, and then by this theorem G is a cyclic group. Then G is a cyclic group, and hence it is abelian. So the center of G, that is ZG, equal to G. For an abelian group, the number of conjugacy classes equals to the number of elements of the group. Since A belongs to ZG, center of the group G, then class A equal to the singleton set A and conversely. Hence the number of conjugacy classes equal to 77, and the number of conjugates of the element A is 1, because this class A, because if A belongs to ZG, then class A contains only the singleton set GA. So here the abelian group this cyclic, so Zg center of G is equal to G. Hence this number of conjugacy classes equals to the number of elements of the group. So number of elements is 77. So the number of conjugates of A is only 1. Hence the correct option is 1. Question C. Let G be a cyclic group of order 40. Then which one of the following is true? G be a cyclic group of 40. Then J equal to what? Correct option is 3. Because know the following theorem. If G be a cyclic group of order m into n, where GCD of m comma n equal to 1, that is m and n prime to each other, then G is isomorphic to P cross Q, where P and Q are two cyclic groups of orders m and n respectively, that is order of P equal to m, order of Q equal to n. Now GCD of 8 comma 5 equal to 1, and Z8 and Z5 are two cyclic groups with respect to set of residual classes, this Z8 and Z5 also, and with respect to the addition modulo 8 and addition modulo 5 respectively. Hence, by this theorem, this G is isomorphic to Z8 cross Z5 option. Correct option is 3. Next question D. Number of non-isomorphic abelian groups of order 2017 whole cube. Now 2017 is a prime integer. Consider all partitions of 3, because the power is 3, which are as follows: these 3, 2 plus 1, or 1 plus 1 plus 1. Thus there are 3 partitions of the power 3. So there exist 3 non-isomorphic groups of order 2017 whole to the power 3, and they are Z 2017 cube, comma Z 2017 square plus Z 2017, because this 2 plus 1, so 2017 power 2, and this 1, or Z 2017 plus Z 2017 Z 2017. So we get 3 non-isomorphic groups of order 2017 to the power 3. Hence correct option is this, 3. Question E. Number of automorphism on Z2 cross Z2. Now Z2 cross Z2 is the set of all residue classes order pair. This class 0, comma class 0, class 1, class 1, class 0, class 1, class 1. Let E equal to class 0, class 0 order pair, E equal to class 0, class 1 order pair, B equal to class 1, class 0 order pair, and C equal to class 1, class 1. Clearly, and this Z2 cross Z2 is the Klein's 4 group V. Each element of this group is its own inverse. An isomorphism of the group Z2 cross Z2 onto itself is said to be an automorphism of Z2 cross Z2. An isomorphism phi maps Z2 cross Z2 to Z2 cross Z2. This from this to this phi is automorphism as well as isomorphism, and same group, so this automorphism is given by a permutation A, B, C, which is the group of permutations of three elements, that is S3. Here cardinal phi equal to E for all phi by the property of isomorphism. For example, if phi 1 is an automorphism on Z2 cross Z2, then we can write phi 1 E equal to phi E, phi 1 A equal to A, phi 1 B equal to B, phi 1 C equal to C. Actually, this is the identity automorphism on this Z2 cross Z2. Similarly, we can find other automorphisms phi 2, that is EABC, the domain set, this is the codomain set EBCA, phi 3 is this, phi 4 is this, and phi 5 is this, and phi 6 is this. Actually, this upper row, this EABC, EABC, all are same. So this image, the EBCA, actually this BCA, this anticlockwise rotation, this CAB, this CAB, and E to E same for all automorphism. BCA, then CAB, and then clockwise rotation, this ACB, and next CBA, and next BAC. So number of automorphism of Z2 cross Z2 is 6, that is this equal to 6. And also note that automorphism of Z2 cross Z2 is isomorphic to S3, symmetric group S3. This EABC are all these, this E equal to this, A equal to this, B equal to this, C equal to this. So correct option, number of automorphism is 6. Number of automorphism is 6. Answer 2. Next question, F. Let F maps R2 cross R2 to R2 be a linear functional defined by T of A, B equal to twice A plus B, A minus 3B, and T star, that is the adjoint of T, and then T star 3, 5 equals to what? Correct option is 2. Let alpha equal to the order pair A, B, and beta equal to order pair X, Y belongs to R2. If T star be the adjoint of T, by definition we can write the inner product of T alpha, beta equal to inner product of alpha, T star beta for all alpha, beta belongs to R2. Now inner product of T alpha, beta equals to this T alpha means alpha equal to A, B, so this 2A plus B, A minus 3B, beta equal to X, Y order pair. So by standard inner product, this is equal to X into bracket 2A plus B plus Y into A minus 3B. Then we can write this equal to A into bracket 2X plus Y bracket close plus B into bracket X minus 3Y bracket close, and this equal to this inner product of the order pair A, B, this order pair 2X plus Y, X minus 3Y. This equal to inner product of alpha, T star beta. So T star beta, that is equal to T star X, Y, this 2X plus Y, X minus 3Y. So T star 3, 5, put here X equal to 3, Y equal to 5. So 2 into 3 plus 5 is 11, and this 3 minus 3 into 5 this minus 12. So correct option is 2. Next question, G. Let the set u1, u2, u3, u4, u5 be an orthogonal basis of R5. Y be a vector in R5. W1 equal to the span of the set u1, u2. W2 equal to the span of u3, u4, u5. If W perpendicular denotes the orthogonal complement of W, then which of the following is false? Actually, wrong statement is this: Y is orthogonal to W1 and W2, and 1, 2, 3 options are all correct. Let Y belongs to R5. Then for some scalars Ci belongs to R, reals I equal to 1 to 5, Y equal to C1 U1 plus C2 U2 plus dot 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 plus C5 U5. Because this is the orthogonal basis of R5. So we can write any vector Y from R5. We can write by this linear combination of this equal to Z1 plus Z2 say, where Z1 equal to C1 U1 plus C2 U2 and Z2 equal to C3 U3 plus dot 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 plus C5 U5. Hence, obviously, option 2 is correct. There are two vectors Z1 in W1 and Z2 in W2 such that Y equal to Z1 plus Z2. Next, this Z1 equal to the C1 U1 plus C2 U2. So this belongs to the span of the set U1, U2 for some scalars C1 and C2. So this span of this U1 U2 equal to W1. So Z1 belongs to W1 and Z2 equal to it belongs to the span of U3, U4, U5. This is equal to W2. Now Z2 dot U1. Z2 means this C3 U3, C4 U4, C5 U5 dot U1. So this C1 U3 dot U1 plus C4 U4 dot U1. Actually, this is the inner product between this U4 and U1 plus C5 U5 dot U1. Now this set U1, U2, U5 is orthogonal because the orthogonal basis. So orthogonal means the Uy dot Uj equal to 0 for I not equal to j. So U3 dot U1 equal to 0, U4 dot U1 equal to 0, U5 dot U1 equal to 0. So Z2 dot U1 equal to 0. And similarly, we can find Z2 dot U2 equals to 0. Z2 equal to this, U2 equal to this, and inner product. So U3 dot U2, U4 dot U2, U5 dot U2 are all 0. Now W1 perpendicular is the set of all those vectors alpha belongs to R5 such that alpha dot beta equal to 0 for all beta belongs to W1. So obviously this equals to the set of all those Z2 belongs to R5 such that Z2 dot U1 equal to 0 because U1 belongs to W1 and Z2 dot U2 equals to 0, U2 belongs to W2. So for all beta belongs to W1. Here Z2 dot U1 equal to 0, Z2 dot U2 equal to 0. So W1 perpendicular equals to W2. And similarly, we can find W2 perpendicular equal to W1. So options 1 and 2 are also correct. So these option 1 and option 2 also correct. So only option 5 is wrong. Now Y dot Z1 is the inner product. Y equal to this C1 U1 plus dot 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 C5 U5 dot Z1 C1 U1 plus C2 U2, and this is equal to C1 square C1 scalar U1 dot U1 C2 square U2 dot U2 and other product inner product this U1 dot U2 U1 U2 dot U1. So Ui dot Uj equal to 0 is the orthogonal basis. The orthogonal. This U1 to U5 are orthogonal. So not I not equal to J. So Y dot Z1 not equal to 0 because this U1 dot U1 may not be 0, U2 dot U2 may not be 0. So Y is not orthogonal to W1. This Z1 this belongs to W1. This Z1 belongs to W1. So this Y is not orthogonal to W1. Similarly, Y is not orthogonal to W2. Hence, Y is orthogonal to W1 and W2, and this is the wrong, false statement here. So correct option is here 4. Next question H. Let T maps R2 to R2 be a linear transformation such that T of 1, 2 equal to 2, 3 and T 0, 1 equal to 1, 4. Then T 5, 6 equals to what? Let alpha equal to 1, 2 order pair and beta equal to this 0, 1, this order pair from R2. C1 alpha plus C2 beta equals to C1 1, 2 plus C2 0, 1, and this is equal to C1, 2C2 plus C1, 2C1 plus C2 for some scalars, this C1 and C2. Therefore, T of C1, 2C1 plus C2 this is equal to T of C1 alpha plus C2 beta. Actually, T of this means this C1 alpha plus C1 alpha plus C2 beta. So T of this means T of this C1 alpha plus C2 beta. Now this T is linear transformation, not F here. This is T. T is linear transformation. So this C1 T alpha plus C2 T beta. Now T of alpha, this T of 1, 2 and T of 0, 1. T of 1, 2 given 2, 3 and T of 0, 1 equal to 1, 4. So we can write C1 whatever into 2, 3, C2 into 1, 4. So this is equal to 2C1 plus C2, 3C1 plus 4C2. This is a linear transformation of T. This is the formula of linear transformation of this T. Next, let C1, 2C1 plus C2 is equal to 5, 6, because this we want to find this T of 5, 6 is what. So write T C1, 2C1 plus C2 equal to 5, 6. Then C1 equal to 5 and 2C1 plus C2 equal to 6. And solving this C1 equal to 5, C2 equal to -4. So this T of 5, 6 equals to put the values of C1 and C2 in 1. So you get 6, -1. Correct option is 1. Question I. Let A be a matrix of quadratic form bracket x1 plus 2x2 plus plus nxn whole square. Then the sum of the entries of A is what? If n equal to 2, then x1 plus 2x2 whole square equal to x1 square plus 4x2 square plus 4x1 x2. And the corresponding symmetric matrix A equal to 1, 2, 2, 4. If n equal to 3, then this quadratic is this x1 plus 2x2 plus 3x3 whole square. This is equal to this, and corresponding symmetric matrix A equal to 1, 2, 3, 2, 4, 6, 3, 6, 9. Hence, for the quadratic form x1 plus 2x2 plus plus nxn whole square, this 1, 2, 3, first row is this 1, 2, 3 up to n n. Second row is this 2, 4, 6 up to twice n. Third row is this 3, 6, 9. So 3, 6, 9 multiple of first row 3 multiply by 3. First row multiplied by 3, 3, 6, 9 up to 3n. And so nth row multiplied by n, this first row multiplied by n. So n twice n, 3n, thrice n, and n square. So sum of the elements of the first row 1 plus 2 plus 3 plus n is equal to n into n plus 1 by 2. Sum of the elements of the second row, this is equals to taking 2 common, so 1 2 common, bracket 1 plus 2 plus n, so 2 into n plus 1 by 2, and sum of the nth row, this n common, bracket 1 plus 2 plus dot dot n. So adding all of these common n into n plus 1 by 2, this 1 plus 2 plus dot 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 plus n, this is equal to n into n plus 1 by 2. So n into n plus 1 by 2 whole square. Actually this is the summation of n cube, sum of the natural numbers 1 cube plus 2 cube plus 3 cube up to n cube. So correct option is 3. Next question J. If the quadratic form x square plus lambda bracket y square plus z square bracket close plus 2xy is positive definite, then what is the correct option? Correct option is 2, lambda greater than 1. The associated symmetric matrix for this quadratic form is equal to 1 1 0 1 lambda 0 0 0 lambda. This x square, so this 1, y square is lambda, so this lambda, and z square is lambda, so this corresponding principal diagonal is 1 lambda lambda. And for this 2xy, so 1 and 1, xy plus xy, and others, this xz, for this xz, no xz, and this yz, no yz, so this 0. And the leading principal minors, this first order minor, this a1, only this element 1, second order minor, this 1 1 1 lambda is corresponding determinant lambda minus 1, and corresponding third order minor, that is the corresponding determinant a, determinant of a, actually this is equal to lambda into lambda minus 1. Now we know if the quadratic form is positive definite, then these 3 minors, leading 3 minors, a1 greater than 0, a2 greater than 0, a3 greater than 0 for third order matrix. This implies 1 greater than 0 obvious, this lambda minus 1 greater than 0, and this lambda into lambda minus 1 greater than 0. So from this lambda minus 1 greater than 0, actually lambda is greater than 1 is the correct option. So lambda is greater than 1 is the correct option. So correct option is 2. Thank you for watching this video.